And welcome back. Now let's actually talk about finite state machines and what we can use them for. You might have seen finite state machines before in other classes. The idea is you have these series of states and transitions, and in this particular picture, we have the output is a function of the transition. So the arrows of the transition. This says, well, when should you make that transition? I was in state 1. When should you make that transition? Well, when you get this input, this particular sequence, and here is my output here. You can also, by the way, have outputs attached only to the states. So I say when I'm in that state, that's my output. Two ways of doing that. You either transition on the arrows or on the states themselves. And we can see how to use combinational logic and registers to convert any finite state machine into a circuit that we can actually build. It's pretty cool. Let's actually take an example. So we're going to play with this on a finite state machine to detect 3 1s. So detectors are really easy to do. We've used those in exams before. It's a nice example. So what it says is when I have 3 1s, I want to output a 1. And then should I continue to output a 1 when I get the 4th one? No, in this particular state, this particular idea, this has to be part of the spec, by the way. You need to tell me what happens on the 4th one. And then usually this input-output example tells you what to do on the 4th one. The idea is the 3rd one, 1 1, nothing. 2 1s, nothing. 3 consecutive ones, there's my 1. 4 consecutive ones, you don't want to have that be high. You want to reset it and be looking for the next 3 1s. So only if you have 6. So there's 6, will it bleep here for the first 3 and there for the second 3. Okay, so let's see if we can actually think about this. What will the FSM look like for that? Well, we're going to only need 3 states for this particular one. You can have more. I can have a lot of redundant situations, but this is the tightest, smallest FSM that will do this for us. By the way, every state, this is a FYI, every state has to have every possible combination of inputs exiting from that state, which means I'm in that state, I have all the possible range of my inputs. I have to have an exit arrow for all of these options. So here I only have 1 bit, my 1 bit is my input. So that bit can have a 0 or 1. So every one of these states has a 0 exit arrow or 1 exit arrow, okay? Here's state 1. If I'm in, I don't even know what this is yet, but state 1 has a 1 exit arrow, there's my 0. And here state 2 has my 1 and my 0. So every state has one of these possibilities. So otherwise it's not a valid. The second thing, and I didn't do this, I wanted to show you how to do this. Every finite state machine should have an arrow indicating the initial state. You just can't have this set of arrows and transitions to not know where to start. You got to know where to start, and usually there's an arrow in, or what they'll often do, I'll just show you this, they'll do a double circle. That's a double circle around that, and that says, okay, that's the initial state. One of those 2 ways is fine. Let's go with the arrow. So it means we're going to start at state 0. And in fact, there's a semantic meaning behind this particular example, the labels of the states. We're going to actually call state 0, state 1, state 2, the number of 1s I've seen so far. So I'm initialized to have seen no 1 so far. You could also initialize to say I say 1, but in this particular case, I'm going to initialize to seeing 0, 1 so far. And then every time I see a 1, notice this, I'm going to transition to say now I've seen 1 1 so far. Now I've seen 2 1s so far. And when I get the 3rd one, it's my 3rd one in a row, I'm going to output 1, that's why this is right here, and then reset to my initial seeing 0 1 so far. So I'm not going to say, well, I stay there. So let's play with this. Here we go. I'm at 0. Okay, here we go. I'm at 0. And I stay at 0 as long as I keep seeing zeros. I see my first 1. Yay, I've seen a 1. Now I'm at state 1. And now, oh no, I see a 0. I'm going to go back to there. So I reset the number of 1s I've seen so far. Same idea. Here I've seen 1 1. I've seen 2 1s. Oh, I go back. Here, the 3rd was not a 1, it's a 0. I reset. I do not output anything. See how this all makes sense? Let's do this. Now I've seen 3 1s. Here we go. 1 1, 2 1. On that 3rd one, I output 1. There's my output 1. Love it. And I reset having seen 0 1 so far. So I go here, seeing 1, after here I'm state 1, state 2, go back to state 0, seeing 1, and there's my 1. Seeing 1, seeing 2, now I go back to 0, there's my second blip. So all that makes sense. Ask yourself, what would happen, how would you modify this diagram if you want to stay 1 all along? So if this is, I see 4 1s, I should output 2 of these guys. If here I want to output 1 solid set. So I basically keep outputting 1 if I continue to see 1s. How would you modify this diagram? Think to yourself of how to do that, of how to modify the diagram to make that happen. And 3, 2, 1. All right, welcome back. So here's how to do that. If I wanted to have this continuous, that basically says, rather than reset to state 0, I should reset to, drum roll, state 2. So I stay in state 2. So if I were to change this arrow and say this now goes this way, now I've got the third one, I output 1 and I stay in state 2 because I've seen 2 in a row. And the more ones I see, if I see another one, I'll stay there. And only when I see a 0 do I reset to 0. So if all I have to do is change this one arrow back to there. That's a great exam question. What happens when I change this one arrow? What different language am I interpreting? Well, it means that rather than 3 1s and reset, and 3 1s and reset, it's 3 1s and then stay high until I see a 0. And that's exactly what would happen. So this arrow would just change back to draw to land in S2. That's all. Small change, and you can make a different language that you're parsing in some sense in terms of the number of ones I'm outputting. How do we build this? We've kind of already seen that the main structure. I've got the pieces already. I've got some combinational logic that can handle inputs and previous state. I've got a next state, which tells me where I'm going to be in the future, and I've got my output. I take a register, this is standard, I just go off the shelf, grab my register, I know how to handle that, and that's going to handle my previous state, and I wire it like this. This is really cool. That register remembers what state I'm in, and all it is you've reset it to the 0 state. It's a nice thing to do, reset to 0. That's nice to have 0 be the initial state always, because then you reset it, it's fine. You don't have to load in whatever the initial state is at 75, but make it 0, that way you load to 0, you reset to 0. And the combinational logic is used to store and figure out what the mapping is, what my next state should be, and also what my output should be. So there's a one-to-one connection between what this combinational logic looks like and my state diagram we saw before. So here it is. This is the truth table for the combinational logic to do that 3 inputs. Let's see what happens. Here we go. Remember the picture, but just try to remember the picture before. Okay, my previous state was 0. If I get 0, I stay in 0, I output 0. In fact, I only output 1 in the last case. Okay, watch. If my state is 0, I get a 1. Now I've seen 1. Remember the semantic meaning of the state number is how many 1s I've seen. I've seen 1. I still output 0. And remember, all these are output 0. If I'm at 1, oh, when I get a 0, oh, I got to reset. So already you can read this and say, oh, right, yeah, look, 1, I reset when I get a 0. If I happen to be at 2 and I reset, I go back to 0. But if I get a 1 and another 1, I go to state 2. So all this is consistent. And then when I get a 1, sorry, if I'm in state 2 and I get a 1, I reset to state 0 and I output a 1. Exactly. So how would I make that change we did? How would I make the change in this truth table to the idea that if I get the fourth one, I want to stay high. Okay, so I figured the 1, stay high and keep outputting a 1 as long as I continue to see 1s. Ready? Pause the video and come back and I'll give you the answer in 3, 2, 1. It was only that last state. Before I was at state 2, I had a 1 and I went to 0. The only change we made is I cross this off and I say, bloop, 1. Now I stay in state 2 and I continue to output 1 as long as I keep getting 1s. That very simple change makes the change semantically on what that circuit is going to be, doing for me. Pretty cool, right? Good stuff, easy. So here's the general model for a synchronous system. I've got this loop, that same picture you saw before is right here. That's the same picture you saw before. It's clocked, I've got some stuff. But now, and the feedback is only within that system. But you can imagine that following up with another series of what it's calculating, what it's doing, and here's the fun thing. You could have optional feedback from this state back in there, which means this combinational logic is not only knowing the next state, but the state after that too. That's fine, you can have that feedback as well. And you can imagine many, many more of these with a lot more lines feeding back to this very powerful system doing something very complex. That's it. Synchronous digital systems. This is what we're trying to say, and this is the general structure for that. Connections of CL blocks separated by registers, I said that. They may be back-to-back, and register CL might be back-to-back as well. Feedback is optional. You don't have to have the feedback at all. And the clock signal keeps that whole chugging through in that way. I love it. In a big picture, this is what we're trying to teach you in these series of lectures. We're trying to build a system. In that system, we're going to have data path and control. We're going to see that in later lectures that are dedicated to data path and control. Here, we're just kind of talking about what happens in the control world. We've talked about state registers. We've done that already. Combinational logic is the next lecture. state registers, you have the register. We haven't really talked about how to build the logic in detail. That's also the next lecture. And how to put that as part of switching networks is all part of that next lecture. So we've kind of done this in this series of lecture, this in the next one. We're going to probably do a little bit of this in the fourth lecture, and then put these together in the series of lectures after that to be able to build a working RISC-V system, a building system that can interpret all the RISC-V machine code we've been producing from our compiler, assembler, and linker. In summary, we're at the end of this series. State elements are used to build memories. We saw that. You can build a register, from a flip-flop, from a little teeny baby flip-flop, you can build a register. From that register, you can think of that as building memory. We haven't talked about that, but we can talk about that a little bit later when we talk about how to build some of these elements. But the same idea, All you have to do is be able to say, rather than one register, which of these kind of small registers am I going to write to? That's, in a way, all that memory is telling which of these registers am I writing to. We think of each memory as just a long of these registers that each have an address. I want to change that one. Boop. Each one of these is just a register at the lowest level. State elements also help control the flow of information. Otherwise, a combinational logic circuit would just have infinite feedback. It'd be too fast. You have to kind of slow down so it's part of the heartbeat of the system. You know that we use D flip-flops to build registers. Clocks tell us if we clock these flip-flops, then they're going to grow at kind of all cha-chunk, cha-chunk, cha-chunk in my pipeline system. We love that. And I mentioned even pipelining for a faster pipeline, a long delay combinational logic, break them into pieces, pipeline it to have a faster clock. We can do that. Smaller clock period. We love that. And they're extremely useful. You're going to see them in a lot of classes. Finite state machines are really powerful ideas. You'll see them in 151A, 152, 164, 172. Lots. You remember I was talking about the language as parsing languages? That's kind of, I'm using 164 speak. If we think about 164, the compiler class in some sense, and programming systems, will teach you how to use a flip-flop to be able to parse a language, and a finite state machine, not flip-flop, but a finite state machine to be able to parse a language. This finite state machine parses it and is able to receive and navigate and decode this particular language. So we can use finite state machines in many different ways. We're all done. See you at the next lecture.